Hello everyone, welcome to this video. In this video, we'll be studying about the sixth property of isomorphisms. So suppose we have some isomorphism which is defined from say that is phi, which is defined from one group G to another group G bar. In that case, we are saying that if we fix some integer k and if we fix some group element B which is taken from G, in that case this equation x raised to power k is equal to b. Here b is fixed, right? K is integer which is also fixed. The value of x, that is a variable. So this represents the equation. This equation would have the same number of solutions in the set G because all the elements x and b, they are taken from the group G, right? So this equation x to the power k is equal to b would have exactly the same solution as x to the power k is equal to phi of b. Now as b belongs to G is fixed, phi of b belongs to G bar is also fixed, right? If that is so, it means that now if we have this equation x to the power k is equal to phi of b, this would give us the values of x which are member of this G bar, right? And here k is also fixed. So both of these equations, x raised to power k is equal to b and x raised to power k is equal to phi of b, they have the same number of solutions, right? So let's have a look at the proof of this result here. We suppose first of all that if A represents the set of all solutions to this equation x to the power k is equal to b, right? So this would form a set. We are calling that set as A. Then what, because this phi is an isomorphism, we know that phi is an isomorphism. So if we take any solution small a from the set capital A, in that case it would satisfy our equation x raised to power k is equal to b because A is its solution. So therefore we would have a raised to power k is equal to b because it satisfies this equation, A satisfies this equation. And moreover, because phi is an isomorphism, so we may write phi a raised to power k as phi of a raised to power k. And what is a raised to power k? A raised to power k is equal to b. So we can write in place of a raised to power k the value b. So from here, if you see that we have phi of a raised to power k is equal to phi of b. So can you see similarity to this equation? Yes, obviously. So here if you compare these two equations, you will obtain the value of x as phi of a. So that means this phi of a would become the solution of this equation here, correct? So this means that is what I have written over here, that phi of a becomes the solution to the equation x raised to power k is equal to phi of b. So this proves that from this set A, which is the solution of containing the solutions of this equation, then if we apply phi onto all the elements of this, then that set phi of A would become the subset of all the solutions to this equation. So there may be solutions which could be there which are not present in this subset phi of A. So let's see, is this phi a forms the set of all the solutions of this, or are there any other solutions which are also the solution of these equations? So let's proceed and have a look at this thing over here. So we have one thing, that whatever is the set of solutions to this equation that has a subset which is phi of a, right? Next, let us take one solution of this equation, and if that solution, one arbitrary solution of this equation, and if that solution is present in this particular set phi of a, then we would say that the set of solutions of equation x raised to power k is equal to phi of b, that is nothing but your phi of a only, where what was this capital A? Capital A was the set of all the solutions to the equation x raised to power k is equal to b. Okay, so for that, what we are assuming, we are taking one element from capital G bar, right? So let's call that element as small q. We are taking this q here, this is a solution to our equation this. So now because this is a solution, so obviously it would satisfy the equation. So from here we would have q to the power k is equal to phi of b, right? Okay, so keep this thing in mind, because q is the solution to this equation, and moreover here phi is an isomorphism, so therefore we may write phi this q as phi of phi inverse of q, because they both of them they cancel out each other's effect. So ultimately we would be left with this q only, which is this q only, correct? So this is one way of representing this q. So therefore, because we have this thing over here, so we have phi of b is equal to q raised to power k, right? And now we may represent q as phi of phi inverse q. So therefore we may express q raised to power k as phi of phi inverse of q raised to power k. So if you compare these this part phi of b, so phi of b, this is equal to phi of phi inverse of q to the power k. So you see, if you pre-multiply both of this equation by phi inverse, so the effect of this would cancel each other, the effect of this would cancel each other, so we would be left with b is equal to phi inverse of q raised to power k. So therefore we would be left with b is equal to phi inverse of q raised to power k, and you can shift this q to the left hand side, or what you can do, we have this thing na, b is equal to phi inverse of q to the power k, so we may multiply on both sides by phi, right? So you see, we have phi of b here, and the effect of phi and phi inverse would cancel each other and it would become the identity operator. So this would be equal to q to the power k. So phi of b is equal to q to the power k here. So what does it imply? It implies that this q is a solution of this equation, and it is written as phi of some element b. So that means this q would belong to this set phi of a, right? The image set of all the solutions for the previous equation. So therefore the thing that we have told, we have been trying to prove that the set of solutions of the equation x to the power k is equal to phi of b, that is nothing but when we apply the mapping phi onto the set capital A, where what is capital A? Capital A is the set of all solutions of the equation x raised to power k is equal to b, right? So from this we get to know that the equation x raised to power k is equal to b in the group G, and the equation x raised to power k is equal to phi of b in G bar, they both have the same number of solutions, right? So this is what we wanted to prove here in this property.